I'm going to be presenting some work we're doing from HHEAR Pilot Study called PFAS Concentrations in Human Milk, a Sibling Study. So we heard earlier this morning from Dr. Romano about PFASs. They're important. There's thousands of them. They're surfactant chemicals pioneered actually by 3M based in Minnesota in the 1950s and used for a variety of products, stain guards, nonstick cookware, et cetera. And so the same factors, unfortunately, that make them so useful, those very strong carbon-fluorine bonds, also make them very difficult to destroy. So they are those forever chemicals. They persist in the environment for decades and in the human body for years as well. So from a standpoint of health outcomes and associated with PFAS, there's links to thyroid disease, kidney and testicular cancer, liver damage and high cholesterol, and for infants, lower birth weights, reduced response to vaccines and other impacts. And so, of course, with many chemical exposures, we know that infants and children are particularly susceptible given their rapid growth rate and unique physiologies. As far as early life exposures to PFAS, we know that there is significant maternal transfer across the placental barrier, such that infants at birth have serum levels similar to the mother's serum concentrations. But interestingly, postnatally, for those who are breastfeeding, the exposure is much higher. This is because breastfeeding is a major PFAS excretion pathway for the mother. As spoken of earlier today, the transfer efficiencies for these chemicals are not as high as for lipophilic pollutants, and so they range from efficiency from serum to milk, like 1 to 2% for our legacy PFASs, but actually could be much higher for some of the shorter chain PFASs that are more recently used. The problem here is that despite that low apparent percent in the milk, even that brief exposure can have long-term impacts on serum levels. So on the right here is a graph from a paper by Helen Godin and her colleagues at the Minnesota Department of Health, where she modeled the lifetime PFOA serum concentration as a percent of adult steady state concentration. What you can see there is that temporary surge during that breastfeeding period that can be 500 to 600 times what the adult's serum concentration is. So some questions that we need to better model the population impact of breast milk PFAS. First of all, does it decline over lactation? And there's conflicting information on this. Probably the best longitudinal study so far is in Norway, where there were 9 women. You can see in the graph on the right that the concentrations of PFOA declined fairly rapidly to 3 months after birth, PFOS a little bit more slowly, but other studies haven't replicated that. So Germany, there was no detectable change in PFOS. In Korea, there was in fact an increase, and in Seattle, PFOS was again higher in those who breastfed less than 6 months. So a decline with increasing period, but that's cross-sectional. Another thing we could use information on is whether or not PFAS declines with parity. And what we mostly have is cross-sectional data on this. The US, as you know, has relatively little PFAS information in breast milk compared to the rest of the world. So in the US, there was a study back in 2008 from Tao and colleagues for their Massachusetts cohort, where they just compared the 8 members of their cohort who had ever breastfed before. And those women had lower PFOA in their breast milk compared to the women who were samples from women who were nursing for the first time. So getting to why us, so breastfeeding and environmental PFAS pollution are both big issues in Minnesota. Minnesota has the highest breastfeeding rates in the nation, very high initiation, and the highest exclusivity rate at 6 months in the country. Also, we've been making the news a lot, given that wonderful relationship we have with 3M Corporation. The East Metro, in particular, of the Twin Cities, is home to that 3M manufacturing plant at Cottage Grove. And there's lots of landfills around there and other groundwater and community water system levels of PFAS that have been making the news, as far as some of them having somewhat high levels. So when Dr. Lisa Peterson, who's our HHEAR Laboratory Hub director, said, "Hey, Ellen, I know you have a milk study. Maybe you should try to go for one of these HHEAR pilot feasibility projects." And so we thought, okay, that makes sense. So what we put together here was a pilot study where the preliminary aim was to quantify differences in PFAS in mother's milk for sequentially born infants, and also look at changes from 1 to 3 months lactation. We have an exploratory aim, which is then looking at the levels of PFAS EDIs in the milk with infant outcomes like weight gain, adiposity, and development. But given where we're at with those analyses and time, I'm just going to focus on our primary aim. About the parent cohort, it's called the Milk Study, Mothers and Infants Linked for Healthy Growth. It's now at 500 mother-infant dyads. We're still recruiting. And what we do is serial milk sampling, infant body composition. That's at 2 sites, including Minneapolis, St. Paul. The women are non-smoking, alcohol-abstaining mothers who intended to exclusively breastfeed, and their infants who are AGA and singleton and term. So the thing that makes this not unique, but particular here is that all the women in the study had to be exclusively breastfeeding at 1 month for their 1 month visit. And so it's a predominantly and fully breastfeeding cohort. In general, the background goals for our study is to identify bioactive factors in milk that are associated with rapid infant growth and increased adiposity. For this HHEAR pilot study, we decided, how do we make use of this amount of money most efficiently? So we decided on a pilot study, which is a sibling design. We had 23 mothers who were in the study twice. So each woman had participated in the study twice, once with each of 2 infants, and each of those infants had 2 milk samples for a total of 92 samples of milk assayed for this pilot study. Those milk samples were collected from a full breast expression, and that was in the morning after an infant test feed, and the samples were frozen at -80 until analysis. Analysis was conducted at the MDH laboratory affiliated with our HHEAR Center in Minnesota, and it was a targeted PFAS panel with 6 long-chain legacy congeners and 3 short-chained, and that was done using liquid chromatography and tandem mass spec. Our timeline was, the grant was funded in June of 2021. Our laboratory received our blinded samples in September of that year. Quantitation was completed in March of 2022, and we're still doing our analyses and dissemination. As usual, concentrations below limits of detection were imputed. We also calculated estimated daily intakes, and we used linear mixed models with the log transformed PFAS EDIs with a random slope for siblings and a little bit of covariate adjustment. Geometric mean ratios were then calculated to compare across siblings. Okay, so getting to this, a little bit of description. So again, we had those 23 women who had 2 babies in the study. They were 29 years of age at average on the first, and then 2 years later, they were back into the study again. The parent study over-enrolled women of higher BMI. So you see that the majority here of women roughly had either overweight or obese BMIs in pre-pregnancy. And then just to be clear, these are the first and second children in the milk study. 65% or 15 were in fact the woman's first child. So we're looking at child 1 for the mom and child 2 for the mom, but for 8 of them, it was actually their second or third child that was the first child in the milk study. So getting quickly to our results, of the 9 assayed PFASs, 4 were detected. Those included the perfluorooctane sulfonic acid, perfluorooctanoic acid, PFOA, perfluorohexane sulfonic acid, and perfluorononanoic acid, or PFNA. And they were detected in 97, 75, 24, and 3% of the samples. So we're really only going to be talking about those and mostly talking about PFOS and PFOA in statistical analyses here. So this is a table that just shows you the mean and max, in parentheses, picograms per milliliter levels for PFOA, PFOS, and the other two. As we know, these legacy PFASs were taken out of the manufacturing. They couldn't manufacture using these anymore after 2002. And so, as we would expect, our levels here collected in 2019 are more similar to the study from Seattle that was just published than they were to the older study published in 2008. So the levels are lower, but about the same as we saw from the study in Seattle. And this figure just gives you a quick overview, a whisker and plot, box and whisker plot. So you can see that the overall EDIs are around 2 to 6 nanograms per kilogram per day, with higher levels in general for the first sibling compared to the second sibling for PFOS, same for sibling 1 and sibling 2 for PFOA, and a little bit of a decline over time. And so drilling closer into that, for those to look at the longitudinal change over time question, we saw for PFHXS a 36% drop from 1 to 3, no change for PFOS rather, from 1 to 3, and a 32% drop for PFOA. But that was only in baby 1. Baby 2, we saw no change for 2 of them, and in fact a rise for PFOA. So what we're seeing here is it kind of depends on which PFAS you're looking at, and depends on the birth order of the child. And then finally, for our parity question or a birth order question, here are the geometric mean ratios for sibling 2 versus sibling 1. So what you're looking at here is values less than 1, meaning that the level of log PFAS is lower for sibling 2 than 1. And then looking right at the middle there, we're looking at the adjusted values. Log PFOA and PFOS EDIs for sibling 2 are only about 35 to 40% that of their older sibling. And then restricting that in the last 2 rows to just the firstborn and the secondborn of the mother. So that number 15, looking specifically at them, you see the same trend, essentially. So lower values, statistically lower values for second than first children. So there were some limitations. Clearly, we aren't assessing those newer Gen X PFAS chemicals. That would be very interesting to see. This is not a nationally representative sample, relatively small sample size, although pretty similar to prior studies. Similar to the 2 previous reports in the US, our study detected PFOA and PFOS in the majority of samples. And some samples also had perfluorohexane, sulfonic acid, and fluorononanoic acid. Milk concentrations were similar to the Seattle study published in 2019. And our study, I want to point out, given the sibling design, is really well and sort of efficient model for looking at change within women, because it takes out of the equation a lot of those features that vary between women of SES and location, et cetera. And so we did see large declines in breast milk PFOS and PFOA across sequential siblings. And we also see some declines in PFOA from 1 to 3 months lactation, but we only saw that in the first sibling. So maybe some of the conflicting results in the literature are because those studies are not looking at birth order. We're going to try to continue to complete our analysis of the infant outcomes And we want to maybe in the future, hopefully leverage more of these biobanked milk samples that we have for the whole cohort. And we could, look at other maternal factors and maybe start exploring some of those shorter half-life PFAS. All right, I just want to acknowledge the funding from HHEAR, which was incredibly helpful. And my colleagues, and especially I want to make a shout out to Whitney Kerr, who's a PhD student at Oklahoma, who did the statistical analyses for these results, and to Dr. Karen Husett at the Minnesota Department of Health, whose lab conducted the PFAS assessment. Thank you.